Okay, so we have just seen what are the equations that we will solve to describe the motion of one electron due to the external fields. And the from now on, when I will have to make a plot concerning the electronic band structure, I will always make that plot using the situation where the electron feels just a small periodic potential. So I will always use here for the drawings the free electron approximation with the potential that we consider to be just a small perturbation. So we will see the gaps, but the main shape of the band structure will be the parabolic one, just for ease of, for simplicity of making the drawings. And if we remember that band structure, we have the more or less this structure with n equal to 1, 2, 3, depending on the band we consider. These equations, let's say, one of the assumptions that are made before using those equations is the one concerning the fact that irrespectively of the initial position of the electron or on the level on this diagram, the effect of the semi-classical equations are not expected to make to induce any change in the index n. So n is supposed to be a constant of motion. So if the electron you consider has an index n equal to 2, even you start to investigate the effect of the external fields on that electron, the crystal momentum of that electron may change depending on the Lorentz force, but the band index will be never, one of the assumptions is that the band index will never be modified by the external fields. This requirement has limitations on E, B, and on the electromagnetic waves. So I just would like to review those limitations, and let's say for simplicity, I give you the final result because the derivation of the result is quite complex. If you want to have more details, all the derivation of the constraints that I'm going to write here is on in the textbook, in the appendix. So concerning E, one in generally requires that the this product that is a sort of, let's say, E is the electric field. Electric field times electron charge is more or less the force, an estimate of the force. A is the lattice spacing, so force times distance is a sort of energy. So that is an estimate of the energy that is transmitted by the electric field to the electron. This should be smaller and smaller with respect to the energy gap squared divided by EF. So also on the right side, you have an energy because you have an energy square at the numerator and an energy at the denominator. And before commenting, I just write down the three requirements and then I make a comment on each of them. Concerning B, in this case, let's say, if you remember at some point, we recall the cyclotron frequency, that is the frequency of motion of one electron when that electron is applied to an electric field, you may associate to the cyclotron frequency an energy just multiplying the cyclotron frequency by h bar. So the equivalent of the energy transmitted to the field to the electron is, even if it's not correct to say it this way, because if you apply an electric field, if you apply a magnetic field to an electron, you have no change in energy for the electron, is h bar omega c smaller and smaller with respect to energy gap squared divided by the Fermi energy. And the last one concerning electromagnetic waves, what you may expect when applying electromagnetic waves to this electronic system is that one electron may jump from one level to another level depending on the energy of the external electromagnetic waves. So if you consider the frequency of the external waves, then you may, let's say, estimate the energy of a photon due to the external electromagnetic field is by multiplying the Planck constant by the frequency of the external wave. If you expect that the application of those waves is not going to induce a jump from the electron from one band to the next one, then you should require that this is smaller than the energy gap. So whatever the initial, irrespectively of the initial level, then if the energy is smaller than the gap energy, then at that point the electron will not be able to jump from one band to the next. And so we have here three requirements, and so the first one, if you, let's say, estimate so if just to fix an order of magnitude, you suppose that the energy gap is of the order of 0.1 eV, and that the Fermi energy is 5 eV. If we suppose that the A is 3 angstrom, we have a limitation over, using the first condition, we have a limitation over E, because E should be smaller and smaller than E gap squared divided by EF and divided by the electronic charge and the lattice spacing. So concerning the condition on E, we have that E should be smaller and smaller with respect to something that is of the order of 10 to the 7 volt per meter. In general, you never apply such a huge field when you make an electric measurement. So in general, the electric field is some volt per meter, 10 volt per meter. If you use a metal, you never apply 10 to the 7 volt per meter to, again, a metal when you measure conductivity or resistivity. You may increase the value of a field if you have an insulator. So in case you're making measurements on insulators, then you should keep in mind that constraint. But in general, again, it's not a problem. So you have to apply really a huge electric field before being able to not fulfill this requirement. So in general, you forget the limitation concerning the electric field. Then if you make the same calculation for the magnetic field, so omega c is EB divided by the electronic mass. So if you put the value of the electronic charge of the electron mass and you divide by h bar, then what you find is that the limitation concerning B should be smaller and smaller with respect to a value that is of the order of 17 Tesla. Now, this is not so really high because if you go to the lab, 5, 7, 10 Tesla are not so difficult to be obtained using an experimental apparatus. In general, you have people that apply fields as high as 45 Tesla to samples. So in this case, you have to keep in mind the constraint, because again, it's not so difficult to apply a field of this order of magnitude to the sample when you when you make an experiment. And the last one, concerning the electromagnetic waves, if you refer to this equation, if you, in place of the frequency, write down C divided by lambda, here you have an upper limit for the frequency that, if you make the calculation using lambda, means a lower limit for lambda. So in this case, as in general, one uses lambda as a parameter rather than the frequency. I just write you the constraint using lambda. So lambda is larger than, okay, I write value, but 0.4 would not be necessary. So lambda is larger than 12 microns. But please keep in mind that these constraints refer to the case to when you want to use the semi-classical equations. So the fact that here we have the lambda should be larger than 12 microns doesn't mean that we may not study the optical properties, because when we study the optical properties, we are not going to study the dynamics of the electron due to the electromagnetic waves. We just want to explore what happens if you are able or not to induce transitions, for instance, over the bands. So in our case, we may then discuss what happens to the optical properties of the system, because in that case, again, we do not want to study the dynamics of the electron applying visible light. We just want to see what is the effect of the application of the visible light of the electrons. So we may accept the fact that visible light may induce transitions. So again, this doesn't prevent the fact that we may discuss the optical properties of the electrons. So if we keep in mind those constraints, one additional thing I would like to discuss before solving the equations is the following. The final point of the discussion will be the evaluation of the current, because at the end, what I would like to do is to compare the conductivity that was obtained by the Drude picture, Sommerfeld picture, to the conductivity that is obtained in the case you have block electrons. So the final step will be the evaluation of J. I just would like to introduce some details concerning this point. Again, in the Drude picture, the density current was just electronic charge times electronic density times electron velocity. In this case, we have that we had to change this value, change this representation into an integral, because we have many electrons to consider that have different velocities. So we have an integral over the first Brillouin zone. We have d3k and d divided by 2 pi to the power of 3, and that comes from the level density in the reciprocal space. The volume disappears due to the fact that the current we investigate here is not the current, but is the current density. So the volume disappears when we evaluate the electronic density, because we need the number of electrons divided by the volume. Due to that, the volume that is included in the level density disappears in this integral. Then the actual number of electrons is represented by the Fermi-Dirac distribution, evaluated using the energy of the electrons, E of n. And then we have the velocity of those electrons, that is 1 divided by h bar E of n of k. If you notice in the integral, we always have the band index. We have the band index within the Fermi-Dirac distribution function, and we have the band index in the evaluation of the velocity. So you may consider that this is the density current with label n. So this is the density current that is due to the band with index equal to n. So this means that when we evaluate the current of the system, we have to discuss the total value of the current for each of the bands that build up the electronic structure of the solid. Just suppose in this integral that f, so the Fermi-Dirac distribution, is equal to 1. So if f is equal to 1, this means that the levels so all the levels are occupied. So what is the value of this integral in case? So j of n is equal to minus c, the integral over the first Brillouin zone of d3k to pi to the power of 3. Then we have just 1 divided by h bar gradient of the energy. The energy is a periodic, E of n is a periodic function of the wave vector. It can be demonstrated that if you make an integral over the first Brillouin zone of a function that is periodic in the reciprocal space, then the value of this integral is 0. And just to, let's say, appreciate why that integral should be 0, let's just see what happens in case we consider free electrons, because in that case, we may evaluate the derivative quite easily. In case we consider free electrons, so pi over a minus pi over a, the energy is a parabola. The velocity in this case is the derivative of the energy. So the energy is proportional to k squared, the velocity is proportional to k. So if you plot in the same diagram the velocity, the velocity is just a line. So the velocity dependence on the wave vector is a line. So in half the first Brillouin zone, the velocity is positive. In the other half, the velocity is negative, and the positive values are equal to the negative values. So you have that when you make the average of the velocity over the first Brillouin zone, the value is 0. So in general, what you have is that if a band is completely filled, that band will not contribute to the density current. So from the point of view of how many electrons do we have to consider when solving the equation of motion of the system, the answer is only the electrons that do not belong to bands that are filled. So as filled, for filled bands, the density current is equal to 0. So this explains, for instance, why for some metals, the Drude picture or the Sommerfeld picture were not in agreement with the experimental determination of the electronic density. because in the Drude picture and in the Sommerfeld picture, they used all possible electrons in the evaluation of all the quantities: electronic density, density current, conductivity, and so on. But if we now look at block electrons, what we see is that even if you use many electrons, all the electrons that used both Sommerfeld and Drude for the calculation, at the end, the only electrons that participate to conduction are the electrons that are not found in field bands. So if in your system you have a field band, then those electrons, let's say, contribute to the system as they keep charge neutrality, but they do not contribute to conductivity. And as we saw when we discussed the number of electrons that can be found in one Brillouin zone, one Brillouin zone is able to contain 2n electrons. So you have n levels in the first Brillouin zone, so you may host 2n electrons, so an even number of electrons. So this means that if you want to have field bands, then only field bands, then the number of electrons that you have in the system should be even. At this point, you may ask, if I pick up the periodic table, if this is fine, I should find metal insulator, metal insulator, metal insulator, but this is not what you find because you have many metals, also insulators, but you have not an alternation of metal and insulator. The problem is that the condition that the number of electrons should be even is necessary to have an insulator, but is not enough to have an insulator, because if the number, if you have an insulator, or sorry, I used insulator without defining what insulator means. I mean, I'm sorry for that. If you have that all the bands are filled, this means that you have no contribution to the current density, because the current density is 0. At this point, if you have a system where even if you apply an external field, you have no charge transport, then in that case you have an insulator. So in general, even number of electrons is related to the fact that you have an insulator. So insulator means that the number of electrons is even. But if the number of electrons is even, it is not said that you have an insulator. And just to visualize that, I just make a two-dimensional plot, because otherwise the three-dimensional is more complicated. If we have a cubic lattice, and let's say what I will do now is just to recall, if you remember, one day we plotted the first Brillouin zone for the cubic lattice. We started for the Fermi sphere, and then we applied the deformation to the sphere due to the fact that the sphere was intersecting the borders of the zone. So now I'm doing exactly the same steps. So if we suppose to have it's not exactly a sphere, but if this is the Fermi sphere, as you notice, the sphere, let me tell it in Italian, la sfera non ha sfaccettature, la sfera è una figura curva. Le zone di Brillouin sono solidi con facce piane. Quindi è molto difficile che una sfera si incastri esattamente in una figura solida con facce piane. Quindi se voi partite da una situazione in cui gli elettroni sono liberi, quindi una sfera, e cercate di far entrare quella sfera in una zona di Brillouin, che in generale non ha facce curve, ma ha facce piane, è difficile ottenere questo risultato, anche se tenete conto delle deformazioni che trovate al bordo. Quindi il messaggio è, col fatto che per riempire completamente una zona di Brillouin, la deformazione deve essere talmente forte da costringere la sfera a deformarsi e ad aderire perfettamente alla forma della zona, è difficile osservare isolanti. È per quello che vedete più spesso metalli nella tavola periodica. Allora, questa è una cosa che non riesco a dimostrare con i calcoli e a farvi vedere con dei passaggi. Quindi è una cosa a cui chiedo di arrivare a voi solo usando la vostra immaginazione. Quindi la domanda è, e altra cosa, questa conclusione è qualitativa, quindi non vi sto dando un criterio quantitativo, ma vi sto dando un criterio qualitativo per capire come mai la probabilità di trovare un metallo è più elevata rispetto alla probabilità di trovare un isolante. Quindi di nuovo dipende dal fatto che se partiamo dal modello elettroni liberi e poi applichiamo le deformazioni dovute al potenziale periodico debole, è difficile riuscire a costringere la sfera di Fermi ad adattarsi perfettamente ad una zona di Brillouin in modo tale da riempirla completamente. A questo punto vi chiedo se, detta in questo modo, la cosa vi permette di visualizzare nella vostra mente questo concetto. So, even for those who are connected, I'm sorry if I explain in Italian, but say I thought that my English was not fine enough to describe properly the things also in English. So, was what I told enough for you to imagine in your mind what is happening, or do you want me to repeat the same things in a different way, or do you have some questions?
Prof?
Sì?
Noi quando in struttura 2, mi spiego in italiano che vado meglio,
Sì.
abbiamo visto nel caso unidimensionale, cioè distinguevamo i conduttori dei semiconduttori e degli isolanti in relazione all'energia di Fermi, sostanzialmente dicendo se taglia o meno una banda, cioè se l'energia di Fermi tagliava una banda si diceva che era un conduttore perché appunto applicando un campo si poteva venire a creare una corrente, se invece stava esattamente tra due bande, eravamo nel caso di un semiconduttore e di un isolante, e a seconda del gap tra le due bande distinguevamo tra isolante e semiconduttore.
Sì?
È grosso modo la stessa cosa, solo vista nel caso 2D, quello che stava spiegando lei?
Allora diciamo, proseguo in italiano. Quello che dicevi torna e ci arrivo fra un secondo, quindi la distinzione fra, diciamo, il grande gruppo, la suddivisione del gruppo degli isolanti in semiconduttori e isolanti a seconda del valore della gap, quello ci sta e ci arrivo fra un attimo. Io volevo solo puntare l'attenzione sul fatto che diciamo così, nel momento in cui mi chiedo cosa deve succedere per poter avere un semiconduttore o un isolante, quindi comunque un sistema in cui le bande sono o completamente vuote o completamente piene. In quel caso ho bisogno appunto che la distribuzione elettronica, la distribuzione dei livelli, riempia completamente una zona di Brillouin. E dato che facendo riferimento anche allo schema che citavi, cioè quello degli elettroni con un debole potenziale periodico, in quel caso parto da un'iniziale distribuzione che ricorda la sfera di Fermi e poi la deformo per tener conto dell'effetto dei piani di Bragg, allora diciamo così, ho maggiore probabilità che questa deformazione non riesca a schiacciare la sfera completamente dentro una zona di Brillouin e ho più probabilità invece che rimangano delle porzioni della sfera in una zona, in una successiva, e che quindi comunque io abbia a che fare con delle bande che non sono né completamente, che non sono completamente piene o che non sono completamente vuote. Viceversa, adesso va benissimo anche la distinzione che citavi poco fa, ovvero se prendo come riferimento la descrizione unidimensionale dei livelli elettronici in caso di debole potenziale periodico, allora se ad esempio l'ultimo livello occupato, a livello di fermi, vi cade qui, scusate, avevo tolto, vi cade qui o vi cade qui, a questo punto vi trovate che nel primo caso solo la prima banda è mezza occupata e mezza no. Nel secondo caso la prima banda è completamente occupata, la seconda banda è occupata per metà. Quindi in entrambe le situazioni avete che il livello di fermi taglia una banda e quindi è possibile individuare un livello che è l'ultimo livello occupato. In questo caso ci troviamo nella condizione di avere un metallo, cioè posso sperare che l'applicazione di un campo produca un contributo per quanto riguarda la densità di corrente. Se viceversa le bande sono o completamente occupate, quindi ad esempio tutti i livelli di questa banda sono occupati, tutti i livelli di questa banda sono vuoti, quindi qui ho tutto occupato, qui i livelli sopra sono tutti vuoti. A questo punto, per il modello semiclassico, tutti gli elettroni che ho qua sotto non possono andare sopra, perché nel modello semiclassico suppongo che non ci sia possibilità di avere transizioni fra bande. A questo punto ho un sistema che ha tutte le bande piene e quindi non ha la capacità di trasmettere correnti, di sopportare correnti. La distinzione poi fra un sistema di tipo superconduttore, scusate, un sistema di tipo semiconduttore e un sistema di tipo isolante dipende dall'entità di questa distanza, cioè dall'entità del salto energetico fra l'ultimo livello libero, scusate, l'ultimo livello occupato e il primo libero. Perché una cosa a cui io quasi mai faccio cenno è il fatto che anche se voi dall'esterno non intervenite con onde elettromagnetiche o con altri mezzi, è possibile che gli elettroni che occupano gli ultimi livelli qua in cima abbiano una probabilità non nulla, a causa dell'energia termica, di saltare e di raggiungere la banda libera che hanno sopra. Ovviamente questa probabilità è più elevata se la gap è piccola e meno elevata se la gap è molto grande. Quindi in generale sistemi dove la gap è molto grande sono isolanti perché la probabilità di avere un salto per causa dell'energia termica è molto ridotta, viceversa i sistemi in cui la gap è più ridotta, è più piccola, allora hanno una probabilità non nulla di avere degli elettroni anche nella prima banda sopra, che non sarà completamente vuota, ma ospiterà degli elettroni che sono appunto, che raggiungono quella banda a partire dagli ultimi livelli occupati della banda che nel disegno che ho fatto io ha indice pari a 2. Quindi diciamo che se uno riesce in 3 dimensioni a costringere completamente gli elettroni a stare esattamente dentro la zona di Brillouin, si trova ad esempio in quest'ultimo caso, quindi tutte le bande piene. Se uno non ce la fa, allora può cadere nell'esempio che avevo fatto in cui ci trovavamo la prima banda quasi completamente piena e la seconda banda con alcuni livelli che erano posizionati vicino ai bordi della zona di Brillouin. Quindi la distinzione metallo semiconduttore isolante rimane, appunto anche sulla base tenendo conto della gap, e in generale quello che mi aspetto è di trovare prevalentemente sistemi di tipo metallico piuttosto che sistemi di tipo semiconduttore o isolante, dato che appunto la condizione di avere la condizione numero pari di elettroni è richiesta per un isolante, ma non è sufficiente a generare un sistema appunto di tipo isolante o di tipo semiconduttore. Ok, torna con quanto dicevi prima?
Sì, sì, grazie.
Ok. Yes, so now I switch back to the English. And so with this idea in mind, so we have limitations concerning E, D, and the frequency of the electromagnetic wave. In addition, all the equations will be applied just to the we may imagine that the equations can be applied just to the electrons that belong to a band that is not completely filled or not empty. So only the bands where we have a number of electrons that is in between, let's say, larger than 0 and smaller than 2n may give rise to a current density that is different from 0. So the first step is to see what happens when we apply an electric field. So the first case will be the application of an electric field uniform over the system, so no modulation in space or in time, magnetic field equal to 0, and no electromagnetic waves, so just the electric field. So in this case, the semi-classical equations are these two equations. And if we just have a look at the second one tells us that the derivative of k is constant. So it's just a sort of motion where we have a constant acceleration. So at this point, we may obtain the equation for k, and h bar k of t is equal minus e times time plus h bar k0. And we also may divide everything by h bar. So we have that k of t is equal to minus e divided by h bar times t plus k0, where k0 is the initial level that is occupied by the electron before the application of the electric field. So the idea in this case is that if you switch on the electric field, the crystal momenta of the levels will shift to the right or to the left depending on the orientation of the electric field. So just to see what happens in the one-dimensional diagram, what we have is that if we consider just one band, if we suppose to have a metal, so the last occupied level, the Fermi level intersects one band. So at the beginning of the calculation, when the electric field is 0, we have an even occupancy of the levels. So half of the levels on the right side are occupied and half of the levels of the left side are occupied. Then when we switch on the electric field, if we suppose that the electric field is applied to the right, then we have a motion of the crystal momenta to the left. So I now exaggerate in the drawing. So the initial, after a time t, we have that, for instance, the occupancy of the levels is given by this diagram. So you have a shift to the left of the crystal momenta. Again, this is an exaggeration. What is a consequence of that? In the initial diagram, the occupation was even. So if you make the integral of the velocity over an even domain of integration, you have that the average velocity due to the electrons that are at the right and the average velocity due to the electrons that are at the left are equal in modulus, but with opposite sign. So you have that the velocity is 0. But in this case, if you have a translation of the crystal momenta to the left, you have no more this even occupation of the levels. So you have more electrons with the velocity that is, let's say, negative in this picture, and a smaller number of electrons that have a velocity that is positive in this diagram. So you have an overall imbalance of the velocity towards negative values. So the fact that now the electron population, that the occupied level population is no more even, but is uneven, because you have more levels occupied on the left and smaller number of levels occupied to the right, is at the origin of the fact that now you may expect to have a current that is different from 0. And please, just let's make an exaggeration. If you now focus on one level, so if you let time t to move from 0 to infinity, what happens to that level? If we, for instance, concentrate on this level, so let's suppose that this is the starting level for the electron. If you let time goes by, as time goes by, you have that this level moves to the left, and as that moves to the left, the level, the velocity that corresponds to the level, as the velocity is the derivative of the energy, is negative, as you are on the left side, so negative velocity. At some point, the level reaches the border of the zone. At that point, the velocity is 0. In principle, the level should jump out of the first below end zone, but for periodicity, you have that what exits on the left side comes back on the right side. So the level exits on this side and jumps in on the other side. When the level jumps in, you have a 0 velocity because you are the border of the zone. But as soon as the level approaches the center of the region, then you have that the velocity is positive. So if you let the level evolve for an infinite time, you have that the velocity of the level changes from positive to negative, positive to negative. So you have an oscillation of the current. In one case, current to the right, in the other case, current to the left, and so on and so on. So in principle, if you apply a static electric field, you should observe not a DC current, but an AC current. Now, I think that you never observed an AC current when applying a DC field. So what is the motivation behind that? The motivation is due to collisions, because T is not allowed to move from 0 to infinity without boundary, because in general, let's say, the system is able to, let's say, survive without collisions for an amount of time equal to the relaxation time. So you do not observe that kind of dynamics just due to the fact that you have collisions in the system. We may just try to estimate what is the amount of time that is needed for a level to move through all the first Brillouin zone. So if we make this question, what is the amount of time needed So what is the amount of time needed for the level to travel through the first Brillouin zone? At this point, if we write the equation as k of t minus k0, that is equal to minus E electric field times t divided by h bar. If we set this kt minus k0 equal to the size of the first Brillouin zone, so 2 pi over A, we may evaluate T. So if we use always 3 angstroms for the lattice spacing and 1 volt per meter, so if A is 3 angstroms, the electric field is 1 volt per meter, then we may evaluate T at T is equal to 0.7 times 10 to the minus 5 seconds. This is orders of magnitude larger than the relaxation time. So this means that the electron will never be able to, let's say, travel through the first Brillouin zone and to change its crystal momentum so that we may appreciate the oscillating behavior. I open a parenthesis. The oscillating behavior was actually observed, but in very specific systems where you remove, let's say, remove is a strong word, but you let the probability to have a collision to drop down to 0. So many requirements, but they were able to observe that. So if the system is, let's say, very ordered, very precise, no defects, and so on, then you may observe that. But in general, this is something you never notice when you apply a DC field. So again, we are not able to observe a DC field, sorry, we are not able to observe an AC current due to the application of a DC field due to the fact that the dynamics of the system is actually a shift, in this case, to the left, but the shift on this scale may not be observed because that is so small that is just a very slight deviation from the initial picture. So in general, again, you do not observe that. Why this translation, sorry, why this motion of the wave vector induces a current in the system? To observe that, we may just refer to the, again, to the usual picture. So the two-dimensional one, here we have kx, ky. If we suppose that, just to make this drawing simple, the initial configuration is the configuration where the electronic levels occupy the Fermi sphere. So the levels, the occupied levels are included in this sphere, and this is the condition corresponding to E equal to 0. If we switch on the electric field, then kT is equal to K0 minus E divided by H bar T. So if I suppose to have an electric field applied in this direction, I have a translation of the sphere to the left. So the levels yeah, the levels translate to the left. Now I exaggerate this drawing. So the final configuration of the occupied levels is this one here. So I have a translation to the left. Thanks to this translation, the level of occupancy is no more even. So what I find is that the electrons that are on this side, on the left side of the Fermi sphere, have a velocity that is directed to the left, as the velocity is the gradient of the energy. So the energy points outward. The gradient, sorry, is a vector that points outward with respect to the sphere. If you look at the electrons on the other side, those electrons, the electrons that are located here, have a velocity that is again given by the gradient of the energy. But in this case, you are closer to the origin. So the energy is smaller and the gradient is smaller because the gradient is proportional to K in the free electron picture. So in this case, the velocity, let's say, is opposite to the velocity of the electrons that are found on the other side, but is smaller in size. So you have that when you evaluate the integral, the electrons, you have a large number of electrons on the negative side, where the strength, where the modulus of the velocity is larger than the modulus of the velocity of the electrons that you find on the positive side. So due to that, the average value of the velocity is, in this picture, negative. So you find again what you, let's say, expect to find when you apply an electric field to a negative charge. So you apply the negative field in you apply the electric field in one direction, but the negative charge moves in the opposite direction. So again, we find the classical result, but in this case, the result is due to the motion of in this picture, the Fermi sphere, motion that induces an imbalance between the levels of occupancy, and due to this imbalance, you have that the average speed or the average current is no more zero, but in this case is negative. In this case is negative. Okay, and yeah, I think it's better for me to stop here because it's more or less 11:30. Do you have comments or questions on this part? Also for these connected or who is connected, do you have questions or comments?
No, everything's fine.
Okay. Okay, so now I stop the registration. Okay, thank you.